Combustion reactions are reactions where an element or a compound reacts with oxygen to form an oxide and produces heat. Hydrocarbons are a special form of combustion, and when they combust with oxygen, they produce carbon dioxide and water. Combustion reactions are oftentimes the most fun kind of reactions that students get to experience in a chemical lab. But sometimes balancing out their equations can get a little bit frustrating if you don't know some of the tricks. The first example of a hydrocarbon combustion equation that we will be balancing is the one shown below, C3H8. When this reacts with oxygen, it forms carbon dioxide and water. We call this a complete combustion reaction if it goes to completion and forms pure carbon dioxide and water. When balancing out these equations, we always leave the oxygen for last. The reason that we do that is oxygen is found in one location on the reactant side, but it is located in both carbon dioxide and in water on the product side. This makes it a little bit tricky. Another thing that we want to look at when balancing out this equation and pay special attention to is what is our hydrogen doing. The oxygen that's associated with water here is going to give us an odd number if we're not careful. So we can never put an odd number in front of water. Let's get started. The first thing that we're going to do is to make our list of how many of each element that we actually have. We have 3 carbons, 8 hydrogens, and 2 oxygens on the left-hand side. On the right-hand side, we have 1 carbon, 2 hydrogens, and a total of 3 oxygens on the product side. Again, we have to remember that we are adding these 2 oxygens plus the oxygen here from the water. This plus sign helps us to know if we're adding or multiplying. We're always going to be adding those together because they come from different compounds. The first thing I want to do before I do any more balancing is I want to check my hydrogen number. This is 8. I know that if I'm going to balance out my hydrogens so that they are even on both sides, I'm going to have to divide the hydrogen on the reactant side by 2, the hydrogens that are on the product side. When I do this, I get an even number, and so actually I'm going to start by balancing out my hydrogens. Normally, textbooks will tell you to start by balancing out your carbons, but if you do that, you might have to backtrack and erase some of your work. So we're going to just do this a little bit differently than the average textbook says. So I'm going to start by putting an even number, the number 4, in front of water. Immediately, that's going to change how many hydrogens I have. I now have 4 hydrogens. It also changes the number of oxygens I have. I now have 4 oxygens in water plus my 2 oxygens from carbon dioxide. So I no longer have 3 oxygens, but I have 6. Again, I'm going to wait and balance out my oxygens until very last. So the next thing I'm going to do is to balance out my carbons. On the reactant side, I have 3 carbons. On my product side, I'm going to need 3 carbons as well. So I'm going to simply place a 3 in front of the CO2, and that's going to change the number of carbons that I have from 1 to 3. And again, it changes the number of oxygens I have. Remember before we said we have 4 oxygens from water? Well, now we have 3 times 2 oxygens from the carbon dioxide. So we have 6 oxygens in carbon dioxide and 4 from water for a total of 10 oxygens. Because that's the last thing I have to balance, I'm going to follow that over to the reactant side. To get to 10, and I have to have a multiple of 2, I'm going to multiply oxygen by 5. 5 times 2 is 10, and that leaves this equation completely balanced. Okay, I know that might have sounded a little bit confusing, but we'll do a few more problems just for practice. A few reminders of what we just did. A few rules. 1, we balanced the oxygen last. And the other big rule was we balanced the hydrogen before balancing anything else. We checked to make sure that the number that we were going to put in front of the water was going to be an even number. So we always are going to check the reactant side to see if the hydrogens are going to give us an odd number or an even number. If it gives us an odd number, we're going to do something special to the hydrocarbon. After we balance the hydrocarbon, we balance the carbon, and then last we balance the oxygen. All right, let's try a new example. Okay, so here's a new one where we have now C2H6 plus O2. Again, we're going to take a moment to draw out our atoms and count how many we actually have. After doing a quick count, I notice that I have 2 carbons, 6 hydrogens, 2 oxygens on the reactant side, 1 carbon, 2 hydrogens, and a total of 3 oxygens on the product side. Again, I'm going to go against tradition, and I'm going to start by balancing out my hydrogens first. When I look at how many hydrogens I have, I'm starting off with 6. Because I have 2 hydrogens in water, I know that I have to multiply 2 times 3 to get 6. That's going to cause me a little bit of problem because no matter what I do to carbon dioxide, I'm always going to get an odd number. And I have to have whole numbers when I am recording my coefficients. There's no way for me to get a whole number when I'm dividing an odd number by 2. So this adding of the 3 isn't going to work for us. We're going to do a little trick here, and that is whenever we have an essentially odd number that we're going to have to write in front of water, we're going to double the coefficient of our hydrocarbon. So that's going to change automatically the number of carbons we have, and it's going to double the number of hydrogens that we have. What this allows us to do is to have an even number of hydrogens when we go to balance. So now that I have my hydrocarbon doubled, I'm going to go ahead and proceed. I'm going to put a 6 in front of the hydrogen to get my 12 total hydrogen atoms. I now have a total of 6. So 6 plus 2, so I have 8 oxygens. And I'm going to go ahead and balance my carbons now. So I have 4 carbons on my reactant side. I need to have 4 carbons on my product side. So that changes the carbons to 4. But it also changes my oxygens. So I now have 8 oxygens from carbon dioxide plus 6 oxygens from my water. So now we have 14 total oxygens. That's the last thing I need to balance, so I'm going to follow that over to the left here, and 14 divided by 2 gives me 7. So I'm going to put a subscript of 7 in front of my oxygen and change this final answer. So 2, 7, 4, and 6 should be the correct coefficients for this balanced hydrocarbon combustion reaction. Balancing out carbon-based fuels isn't always as complicated. Sometimes you'll have equations like this, where you have a hydrocarbon that will actually have O in it. And this is actually kind of nice, because now when we're looking at our oxygen here and here, they're going to add up to be an odd number, which is the same thing that's going to happen when we add the oxygen here plus here. So we can actually start equations like this where we have a carbon-hydrogen-oxygen compound by balancing out the carbons, then balancing out the hydrogens, and finally balancing out the oxygens. All right, so let's start again by counting out how many of each element that we actually have. We have 9 carbons, 10 hydrogens, and 3 oxygens on the reactant side, 1 carbon, 2 hydrogens, and 3 oxygens on the product side. Then we're going to start by balancing out the carbons. So I'm going to place a 9 in front of CO2, and that is going to change my carbons to a 9. And my total oxygens, I will have 18 plus 1 from the water, so I have a total of 19 oxygens. Again, in some of those other ones that might bother me, but for right now, it's going to work out pretty well. On the reactant side, I have 10 hydrogens, so I'm going to place a 5 in front of the water, which gives me 10 hydrogens. I'm going to again recount the number of oxygens that I have. I have 9 times 2, so 18 plus 5, which gives me a total of 23 oxygens. Here I'm going to do something special, and that is I'm going to subtract out 1 oxygen. The 1 oxygen that I'm subtracting out comes from the one oxygen that's attached to the fuel on the reactant side. So 23 minus 1 gives me a total of 22 oxygens that I have to then account for in my oxygen gas molecule. And so 22 divided by 2 gives me a total of 11, and that should be my balanced equation. I want to end with one final example of a combustion reaction that is important to all human beings. That is the combustion of the compound glucose. This process happens in your cells, and it is what is helping to fuel your body and allow you to do this kind of work. C6H12O6. We have a total of 6 carbons, 12 hydrogens, and 8 oxygens as the starting reactants. On the product side, we have 1 carbon, 2 hydrogens, and 3 oxygens. Again, this is a case where I'm going to just start by balancing out my carbons, then my hydrogens, and I'll finally balance out my oxygens. So working through this process, I now have 6 carbons. I'm going to not worry right now about balancing out my oxygens or counting them until I'm done with my hydrogens. So I have to put a 6 in front of my hydrogens to get a total of 12 hydrogens. And now I'm going to take the time to count my oxygens. So I have 6 times 2, so 12 oxygens, plus I have 6 oxygens from the water. And you can see that right here. So 6 oxygens from the water. Okay, let's get rid of that original 3. Before I go and write in my coefficient on the oxygen gas, I'm going to pay very close attention to how many oxygens I actually have in glucose to start off with. So I have 6 oxygens that are already being accounted for in the reactant. So of my 12 plus 6, I actually can delete out 6 of them because they're already being counted for in the glucose. That leaves me with just 12 oxygens that I have to account for. So 2 divided by 12 is 6, and that's going to balance out my oxygens. I'm going to have 18 oxygens on my product side, and I will have 18 oxygens on my reactant side.